and this recording will be available shortly after we finish. I'll add the link to the recording to the content outline that we've been looking at online. And so today, what I have planned for us to do is take a first dive into building our own model of the spread of COVID-19 in a space. And we're getting a little bit of a later start. So I had imagined spending a bit of time at the beginning talking a little bit more about the segregation example that we looked at last time and maybe considering extensions. And I think what I'll do for the interests of time, so that I don't keep you well beyond what is fair and kind on a Friday afternoon, I'm going to let that aside. And those of you who are interested in talking more, please visit me in office hours. And I've added the link to my calendar to the content outline. You can click on the link, find my open appointment slots, and make time, and we can talk as much as you'd like. So for today then, I'd like to get through a couple of things, which are to think conceptually about COVID-19, to think operationally about how we can build some basic tools in NetLogo, get a little bit of a start there. And depending on how far we get along, maybe we will start to build some experiments in the NetLogo platform so that we are learning as well how to inform the questions that we've asked as part of our modeling exercise. There's a question here about the recording. So once we're finished here today, when I've received the recording, I will add the link to the recording into the document that has been shared with you, which is our content outline. I can pull it up here. And I'm going to share my screen at this point. I'm going to share my whole desktop. There we go. And so this document, and I'll add it into the chat again. Oops, daisy. This document here, the recording for the first session is linked to right here. So this is the content that we had in our first week. And when I got the recording set up, I added a link to it here, and I'll do the same thing here today. So once we finish today, I'll put a link to it here. So as I mentioned, I think probably in the interest of time, I might set aside some of our detailed NetLogo discussions. But for those of you who are interested and want to do more, again, you can link to my calendar right here, set up an appointment to meet, and we can talk some more. So what I'm hoping we'll get through here is a little bit of talking conceptually about COVID, and I'm going to use the Kumu platform that we introduced last week, and then a little bit of first basic steps in NetLogo. And again, in the interests of sort of space and time, there are a large number of us. I do encourage you to ask questions as we go. Feel free to write into the chat, or if you're comfortable to do it, unmute, feel free to ask a question and then mute again. So I've set up a blank map, similarly to what I did last week in Kumu. And I'm just going to move it so that I can see here. I want to start us off with just a basic conceptual model that we'll add to. And the idea here, again, going back to what we discussed last week, is that we're identifying things that are related and important to address our question in order to know whether or not they have a place in our model. And so there are a range of really interesting questions you can ask about COVID. But I think some nice starting questions are simply, how does COVID spread? How can we stay safe from COVID? And use those as a base to think about some of the basic building blocks we might need. So if it's all right, I'll start off with a couple of elements we might need. And I'm going to do my best in this Kumu framework to represent ideas in kind of I'll say a noun form. Things that we can think of as nouns, things we can have more of or less of. And we're going to connect those ideas with arrows. And those arrows, if you recall, will indicate whether one thing changes in the same direction or in the opposite direction. And it'll help us identify key connections and feedbacks. So one of the things that matters a lot in thinking about COVID is the number of susceptible people we have. And what's the other key complement to this? We have people who are susceptible to COVID. And what's another important group of people here?
Infected.
Testing. Apologies. I think I heard testing. I could be incorrect. I apologize. But yeah, testing is going to be a key component of this modeling framework.
Infected.
I'm so sorry. Infected. Yes. Infected people, the complementary group. And so I'm just going to click. Every time I'm adding an element here in Kumu, I'm using the keyboard shortcut E to allow me to add an element. There we go. Okay, infected and recovered. Perfect. Thank you. So infected people. And right. So susceptible people, infected people, recovered. And in some cases, as we know, not everybody survives being infected with COVID. And so we will have a population of deceased people. So these are key concepts for us, and they're connected in some important ways. Importantly, oops. Infected people are connected to deceased people. I've added this connection, and I'm just going to specify here that this is a positive connection. The more infected people we have over time, irrespective of other changes, likely the more deceased people we will end up with over time. And the same will be true for us with recovered people. And I'm jumping through this a little bit quickly. I've spent some time working in Kumu and I'm comfortable with the interface, but if you have any questions about this, please feel free to ask. So the more infected people we have over time, some of those will recover and some of those people will die. There are a couple of other key linkages that matter here. How is it that susceptible people and infected people come to mix? What happens? I'm sorry, would you repeat the exposure, right? Yeah. So that perfect. So let's represent exposure. Oops, I don't want connections. So we'll call this exposure to infected people. And the more susceptible people we have, the more overall exposure I imagine we have of those susceptible people. As well, the more infected people we have, the more exposure I expect us to have. So far, I've got all of these blue, positive, same direction lines. Okay. And we've got part of our model mapped out here. And here's where it's going to get a little bit interesting for us. We're going to add to this several times over the next couple of weeks as we start thinking about behavior and response. For now, we're going to keep it really basic. But the key thing, well, two key processes matter for us here today. One of them is that more exposure is going to lead to more infected people. And what we have here now is what we call a feedback loop, as we introduced last week. In more infected people means more exposure means more infected people. So this is a positive or reinforcing feedback loop. And this is the loop that's driving that rise in infections that we've all seen in different times along the last year in different places. Small number of cases start to shoot up. It looks almost exponential at first. And in fact, that's really what it is. And so this is this important growth loop. But it doesn't go forever. What happens? The more people that get infected, what changes over time? There are many things that lead to the slowdown of infections, but there's one really fundamental, important process that's already captured in what we have in our map here. As we have more infected people, what happens to the number of susceptible people?
It reduces.
It reduces, exactly. So if we capture that in here, infected people to susceptible people, this is, for us in our model, this is the first time we're representing an opposite direction connection, and that shows up in red. The more people that get infected, the fewer remain susceptible and uninfected. And so this is an important balancing loop. As more people become infected, fewer are remaining to be infected. And so the number of infectious interactions reduces. And so that's the competing process that leads our massive growth up to some kind of a peak and eventually some kind of a decline as there are fewer people remaining to be infected. Lots of other things to think about, lots of things that can change the shape of that curve. But these two loops here are enough to get us started and help us learn a little bit about what we see in a COVID problem. Are there any questions about this model? And I'll add the link here. So as we move forward in the next couple of weeks, whenever we talk about something we want to bring into our model, we're going to think about how it fits into this systems perspective here, so that we're answering the questions for ourselves before we start writing code of, does this matter for us and how? Okay. I'll keep watching the chat, and please feel free to ask questions as we go. But what I'd like to do now is open up a blank page in NetLogo and try and get some of these basics in here. So here's an empty model. Okay. Brand new empty model, and I'm going to make it a little bit bigger for us. Whenever we open up a new NetLogo model, we always are given this big black square that represents our two-dimensional space, our world. It's an inalienable part of NetLogo models. It's there, and it's where all of our agents will live and do the things that they have to do. And I'm going to be able to switch between this front interface or kind of dashboard screen and my underlying code just by moving between these tabs at the top. And eventually, if we're being good modelers, we're going to document what we're doing in our model here in the info tab. Okay. So some of you may be doing this at home on your own screen. Some of you might try and do this a little bit later on. The model that we get to today, I'm going to share on our document, so you'll be able to access it. And we're going to record all of our steps here now. All right. So when we looked at the segregation model last week or 2 weeks ago, we saw that all of the different things happening in the model were organized in what we call procedures. And we're going to do the same thing here to set up a really basic model of COVID transmission, we're going to have a procedure to initialize our space, to put all of the variables in place that we need. And then we're going to have a procedure to run the model in each time step. And the likelihood is we'll write little procedures inside that go procedure to do all the specific things that we want agents to do. But enough of me talking. Let's just kind of get on and do it. So you may remember in all the NetLogo models that we looked at, we almost invariably saw a couple of buttons called setup. And you'll note here, I dropped a button down and I was asked to specify what commands would be called when we click that button. And I typed the word setup, and by default, that showed up as the display name. And that's really helpful. It means I don't have to write things twice. I'm just gonna click OK. And it shows up here as red. And that red is NetLogo telling me, I don't know what setup means. What does that mean? You haven't told me. So we'll get there in just a moment. I'm going to drop one other button down first. And that's going to be our go button. Same thing. I've told NetLogo that these two buttons, this one calls a procedure called setup, this one calls a procedure called go, but it doesn't know what it is. It says here, nothing named go has been defined. I'm going to go to my code space, and I'm going to define those procedures. And the syntax in NetLogo for defining procedures, to, setup, end. And here you'll see the letters show up in green. I'm going to make these a little bit bigger. So to says, I'm starting to define a procedure. This is the name of the procedure. Everything that happens in here is stuff inside that procedure, and the procedure ends right here. I'm going to do the same thing for our go procedure. Okay. And I'm going to click the check mark here, which is a little tool that lets NetLogo look in and see if there are any mistakes. I shouldn't have any mistakes because I haven't really done anything interesting yet. But now when I go back to my interface, NetLogo's happy. This text is in black now, which says, yep, I know that you're calling something there. And I can click on these buttons and ta-da, we're running a NetLogo program that doesn't do anything, but it has no mistakes. So great. Let's get ourselves started. Let's build a model that has agents in it, and then let's have them do things. So the first thing that I'll do here, I'm going to use a built-in NetLogo command called clear all. And if it's helpful as we're going, a reminder that you can pull up the NetLogo dictionary online, and all of the built-in commands are listed for you here. They're organized by what objects they apply to. So all of the commands that are sort of member functions of our turtle agents are here. Those that are sort of member functions of our patches are here. Links here. And then you may recall us talking about agent sets, and this is one of the strengths of NetLogo, is grouping agents together in sets and asking sets of agents to do things at a time. All of those commands are here, and so on and so on. So as we're going, if you see me write something and I don't explain it, you can always look for it here and get a sense of how to use it. So clear all is a built-in function that tells NetLogo, clear everything that was there before. So for instance, if we'd been playing with our model and we'd run it before and some of our variables had been set, clear them all. The other thing we're going to do is we're going to use a built-in command called reset ticks. And so ticks, you might recall from last week, are our time step. And every time we run the model, we run it for a step, it counts. We get a tick count. And when we start a new model, we want to go back to 0. So we're going to reset our tick counter. Okay. I'm going to check my code. No problem so far. Great. Still not that exciting. So probably the best way to get exciting real fast is to put some agents in our model. Now, by default, you may recall, all of our agents that move around are called turtles. But if we're not happy with that, we can assign different breeds. We can call turtles different things. And in our case, we probably want to call them people. And the way I'm going to do that, up here at the top, before my first procedure, there are a few little bits of code that I can add to describe global variables, to describe different breeds, and as well to describe particular properties that I want to assign to those breeds of agents. So I'm going to type breed, and you see it shows up in green. NetLogo understands it as this basic procedural part of the language. And I'm going to open a square bracket here, close it. And inside those square brackets, I'm going to say people, the name of the breed that we're going to define as people, and an individual agent within this breed is a person. And that's it. NetLogo already understands what I'm doing here. It knows that I'm just renaming turtles to be called, or I'm naming a particular kind of turtle, and I'm going to call it people, singular person. And what's helpful now is that all of the turtle commands that I might use the word turtle, and you can see there's a few here in the NetLogo dictionary, breeds at, breeds here. All of these, if I now use the word people instead of turtles, NetLogo will understand me just fine. And in fact, the command for creating new agents in the setup space is simply create dash people. Okay. And the syntax for doing this is now to specify the number of people that I want to have, and then give them a set of commands. So I realize I haven't decided how many people I should have in my model. So let me, yes, I know. So NetLogo is telling me, I'm trying to leave the code space, and it's telling me that I haven't done this correctly. Absolutely. Thank you, NetLogo. I want to define a global variable that is the number of agents, the number of people we should start our model with. It could be 5, could be 50, could be 100. But I want to put it on the interface. I'm going to choose here, I can choose a slider. I'll put it right here. And what's nice about this is we can define a global variable here in our slider, and I'm going to call this number underscore people. And we'll start maybe with at least 1, and maybe at most 200. By default, it's going to start off with 50. I'll put a unit of people. Okay, so now on my interface, I have this slider that is this number of people. I can slide it up and down. When I go to my code now, I'm going to finish this command, create people, number people, and then open square brackets, close square brackets. What goes in there are going to be the instructions for all of these new people that I've created, and we'll set those in a moment. But right now, let's just double check. Yep. Okay. Everything looks good. I'm going to make a little bit of space here. And I'm going to give a couple of instructions. When I run this now, those of you who are trying this at home, you can try this. I'll click setup, and it made a whole bunch of people right here in the middle, just all sitting on top of each other, uncomfortably. So very quickly, I'm going to ask them to go somewhere else. There's a command for agents, set XY, and you can see it right here. Set XY is one of the turtle specific commands. It has this syntax, set XY to be this X coordinate and this Y coordinate. And what I want the agents to do is just go somewhere random. And it happens that there are commands to randomly draw an X coordinate and a Y coordinate that fits in the world, and these are those. And you see, as soon as I type them, it shows up in purple. It's, again, NetLogo saying, I hear you, I know what that is. set random X core, set random Y core. Okay, I'm gonna check that. And so now when I set up my model, I've got all these beautiful multicolored agents. We've called them people, but they just look like triangles all over the space. Can I answer any questions for you? And can I just do a quick check? Am I going painfully slowly or am I going very, very quickly?
Yeah, going on well.
Are we doing okay?
Yes.
Okay, perfect. Thank you. I'm so sorry. I didn't quite hear you the first time. All right. So we've got a model. We've got agents. They're not doing anything. Let's have them move around our space. And then maybe let's have them maybe be infected and be spreading virus in the space. Okay. So we've set up our model. I actually don't like that they're all multicolored. I think it might be helpful if maybe we set them all to be one color, and I can do that. Again, all of the instructions inside this block here are instructions for the new agents that we just created. I'm going to ask them to set their color. Again, the color shows up in purple. It's a built-in property that NetLogo understands, and I'm going to let them all be green for now. So now when I set up my model, good, they're all green. And ideally, as model builders, something we want to build skills at doing is making changes that we can test. And so ideally, we don't make too many new changes to the model that we can't test and observe whether it's worked the way we expected. So otherwise, we run into problems where we've made lots and lots of changes. And if we have a problem, we don't know which one was the problem. Okay, so I think that's good enough for now. We're going to let them be green triangles for now. And maybe when they get infected, we'll let them be, I don't know, some other color, blue, red, yellow, whatever we like. So let's imagine in this world that when we start running, there's some small number of people that are infected. And I don't know how they got infected. Maybe they went on a trip, or maybe they came and they're visiting from far away, but they've brought in this infection. And those are the infections that could be passed on to other people in our space. So once again, I'm going to define that number. I'm going to make a slider for it. And I'm going to call it number initial infections. And I don't know how many. Maybe we'll start off with as few as 0 and maybe a maximum of like 5. Maybe I'll use our unit of people here. So now we have a global variable. And what I can do now in our setup, after I've made our agents, and maybe this will show a little bit of the strength of NetLogo, I'm going to set this random, it looks like 3 people start off infected. Let's let 3 of our people be infected. And the way to do that is that we as the observer are going to ask some of our agents, and specifically I'm going to ask n of, so n refers to the number of, and this is a built-in command that is now expecting me to give it a number, and that is, I forgot what I've called it, number initial infections. Number initial infections. So ask n of number initial infections people. And when I use people here, NetLogo understands this to be the set of all people in our model. So I am asking of all of our people some number, which is the number of initial infections, to then do something. And what I'm asking them to do is going to be defined inside these square braces. Okay. And what I want them to do is be infected. So in order for that to happen, our people have to have a property of whether or not they're infected with the disease. And later on, we probably want to represent them as recovered or immune or vaccinated or all these other things. What it requires us to do is write a little bit of code up here called people own. And you may remember this from the code we looked through in our earlier code examples. Here is where we are going to define any additional properties that are specific to our people. So there are lots of member functions and properties that are specific to turtles and agents in general. Here's where we're going to add things that are just for our people. And I'm going to say that there's a property called infected. Maybe I'll use a question mark here, just as a little indicator for myself that this is probably like a true false question. And now that I've done that, all of our people have this property of whether or not they're infected, and I'm going to set infected question mark true. So people can get infected. Now these agents are infected. Okay. And I don't know what color we should let our infected agents be. Maybe it's yellow.
Red.
Red, sorry, did you say?
Red is the good color for infected.
Okay, we'll go with red. Okay, so we'll set their color to be red, and that lets us know that they're infected. So now when I set up our model, right, every time I run setup, we're getting a new bunch of agents, and 3 of them are infected. So far that doesn't mean anything, but we're getting there. Okay, we've got some basic stuff down. We've set up a lot in our model space. And I think maybe that's enough in the setup for now. Let's start making this a dynamic model where things happen. Okay. So our other procedure is our go procedure. And one of the things that has to happen in this procedure is that we advance the time. So in probably the last thing I'll do every time we go through our go procedure is move the ticks. So the command here, tick, just says advance the time step. And now that I've put that in here, when I run our model, if you just look up here, our ticks are counting over time. Oops. Every time I click this button, it's advancing the time step once. And you may remember that we have the option of making this a forever process. So now I've clicked this box here, forever. And so now when I click this button, it's just going to keep repeating itself. There. Huge amounts of time are passing. Nothing else is happening because we haven't told the model to do anything. Okay. So maybe the first thing I'm going to do is have people move in the space. Okay. So I think my go procedure could get complicated pretty quickly. I'm going to try and make good use of comments as we go. So comments, for those of you who are programmers, you've come across them. Every language has a character that you can use. Here it's a semicolon to tell the computer, ignore whatever you see after this. It's just notes for me. So I'm going to make a little note here, and you see it shows up in gray, that people move. And so that's going to let me know when I read this code later what I was doing there, because sometimes it can be hard. So I'm going to let them move. And now that I'm here, I realize I need to decide, well, how quickly do they move? How many spaces do they move in a time step? I'm going to go ahead and define another variable. And maybe you're seeing how quickly we can accumulate numbers and parameters in a model, assumptions. So this is going to be the number spaces move tick. So this is the number of spaces forward that an agent should move in one time step. And maybe they sit still. Maybe it's 0. Maybe it's, I don't know, 5, 10. We'll let it be 2 for now. I'll call this patches or spaces. a number spaces move tick. And so for now, let's just say we use the built-in command forward. So this is right here in our turtle related commands, forward number. And that means that the turtle or the person or whatever it is going to move forward by that number of steps. So forward number spaces move tick was the name that we gave, I think. Yep. Oh, whoops. Okay. That logo's highlighted a problem for me, and that is this, that forward is a turtle command and tick is an observer command. So if you get into working in that logo, you'll get comfortable with this, but there are different spaces and different commands for different spaces. So I need to ask the people to do some set of things for me. Okay. There we go. So now inside my Go procedure, I have a little block here that is the set of things I'm asking people to do. And then once I've finished asking people to do things, I'm ticking the time step. That should work just fine. All right. Are you ready for this? This is where the world's going to get exciting. Here we go. And I'll slow this down so that it looks a little cooler. Here we go. So now we have agents not really moving around, kind of just moving in straight lines. We can build on that. But let's just congratulate ourselves for now. We have agents moving around in the space, and some of them are infected. Okay. And I have about, I'd say probably about 30 minutes, 35 minutes left of coding time. I don't know how much more of your brain power I have because it's Friday afternoon. So let me just do a quick check. We're all good? Are there any questions I can answer up until now? Let me turn on and I'll ask a question to you guys. I've been making this point of adding in sliders, giving them a name, giving them a range, and then using those values. But one of the things I could just do is I could just say, go forward 2 spaces. I could just leave this and the model would run just the same. I could just throw a number in there. Why wouldn't I do that? Does anybody have an idea why that? Some of the reasons why we might not want to do that. What might be a problem that comes up if I just throw a number in there and then I pass the model along to you and say, here's my model, and you look at it. So you can imagine if I throw this along, you might look at it and say, what does 2 mean? Why did you put 2 in here? What does that mean? Why isn't it 3? So one thing is using variable names instead of numbers helps communicate what we're doing. Another thing is that it organizes for us all of the numbers we've assumed so far. I get to put them in this one space. So we know that this space is where all of my assumptions are. And I can play with them and I can change them here. And I don't have to go into the code and erase a 2 and put a 5. So that's another good reason. I put all of my numbers in one spot and then I just refer back to them. And this is an important principle when you're building models and building computer code. Instead of copying numbers and throwing them around and forgetting what they are, it's really good to define them all in one space and then refer back to them. And what can be really helpful is then, if, for instance, I need to use these numbers in lots of different places in the model, like if I need to use the number of initial infections in 2 or 3 different procedures, then I always just refer back to the same place. And if I make a change, I don't have to change it in 5 places. I just move my slider, and every reference back to that will adjust accordingly. So that, in case any of you are wondering, is why I'm making this point of building a slider and putting it down here. And I know it's slow, but it's going to make our model more readable for us as we move forward. Okay. What next? We have people who walk in straight lines. Why don't let's fix that. People don't walk in straight lines. People turn. Well, it's a big part of being a person. It's turning around. So I'm going to suggest we do this. In a given time step, when we're walking, there's some likelihood. Oh, sorry, there's a question here. What happens when the number adds? So is this a question about any of the numbers that we use here? So we haven't had to do any operations yet, but we absolutely can. We can add numbers. We can add variables together. All of the things you could imagine doing in basic, arithmetic, you can easily do here. And we'll have a couple of moments along the building of this model where we'll do that, and you'll see how simple it can be to do arithmetic here. One of the things that's unique about NetLogo is that there are fewer contexts where you'll use an equal sign to specify that something is being summed up than you would in other languages. Okay, what I'd like to do is have our agents move, and I'd like to say they're just going to walk in a straight line, and then with some likelihood, maybe they'll turn around. They'll turn to some other random heading. Okay. And I don't promise you that this is the best way to make agents move, but it's a way to make them move. So this is, again, a bit of this process of I'm going to define a variable, and this is going to be the probability of turning. Probabilities are always numbers between 0 and 1. So I'm going to let this be 0 and increment it by 0.01 and let it go to be 1. So anything from I never turn to I'm guaranteed to turn. Start off with maybe a number like 0.2. And probabilities are unitless. Okay. And so in this move now, I'm going to do a test. So once we have a probability, we can run a test to see in a given turn, do they turn this time? And we'll do that by drawing a random number and testing to see if it's below our likelihood. And those of you who have taken statistics classes and done like t-tests and identified significance, you're probably more familiar with this. But if we set a probability of turning at say 0.2 or 0.1, and we draw a random number and it's less than 0.1, then we'll let our agent move. And what that means is about 10% of the time, or 20% of the time, depending on how we set that, the agent will turn. That's all we have to do here. So here's how we write a test. We're going to use an if statement. And if-else statements are ubiquitous across programming languages. They include a conditional test, they include a logical test, and then a conditional statement, a thing that will be done if the test passes true. And for us, we're going to use the built-in function random float. If random float 1, and for those who are interested in the math section down here, random float number will draw a number between 0 and the number that you state. So random float 1 gives us a random number between 0 up to, but not equal to 1. So if this random number that we've drawn is less than, I forget what I've called it, prob turn. If random float is less than prob turn, then we do something. And inside this block will be the instructions for those agents if we've passed this test. if we've determined that we're going to make a turn. And the various commands that relate to how agents move are here in this list. And we're going to use this face XY command. And this just tells the turtle to turn and face that particular point in the world. So face XY, and we're going to use these same random X core, random Y core commands that we used earlier. So if we pass this test, then randomly turn. And then we move to the next line of code, which we've already specified, which is to walk forward. So here we go. Set up our model. Run our model. Now, agents are turning around in space. And if I make it more likely that they turn, we should end up seeing them more likely to just be going around in circles. So now we have a bunch of agents moving around the space, turning around, not really interacting, not bumping into each other necessarily, but moving around. Okay. I'm going to save this. Save as, call this COVID day 1, just so I don't lose it. Okay, agents running around in space. Some of them are sick. What does that mean? Some of our agents are sick. Now, there are a few different ways we can go about modeling COVID. And some of it kind of depends on the scale, the spatial scale, the temporal scale that we're interested in. And that's a conversation for us to have next week. But for now, we can imagine this as very simply, these are people sharing a physical space. They're walking around. And those who are infected are shedding virus into the space around them. And as other people walk through that virus, with some likelihood, they're going to get infected. And probably the more virus that is there, the more likely it is that they are to get infected. Does that have some intuitive sense to the group as a way to think about this? It's one among many ways to model this, but it's not a bad way to start. So if I go about this, if I want to model that people who are infected are shedding virus into a space, and that virus is accumulating, and presumably over time it dies or disappears. And as people pass through it, there's some likelihood that they get infected. Any idea of some of the numbers, some of the assumptions I need to build into the model to make that happen?
People are interacting freely.
The likelihood of people interacting? Did I hear you correctly? Apologies if I didn't. Did I hear that correctly as like the likelihood of people interacting? Yeah, so people interacting freely here. I guess the way we think about this, it's almost like they're just walking around in the space. And we haven't yet built in anything to represent the idea that maybe they stop and talk to each other or they shake hands or anything like that. They're just walking around sharing a space. and there's virus in that space from those who are infected. And so the method I'm talking about putting in here is very much a physical space mechanism, whether they talk to each other or not. They're sharing a space, they're going to spread virus, and they might get sick. So a few things that I probably have to throw in to make this work. I probably need to have, for instance, something I'll call viral load. And this is some, I don't know what the units for this would be. I don't know what the numbers would be, so I'm just going to make them up for now, and we can come back to this. But some measure of how much virus people drop in a space in a given time step if they're sick. And then once they've dropped it in a space, I need to capture a few things: how it spreads, as well as how long it persists. So I'll call this viral lifetime. And again, this is the number of time steps that we expect virus that's been dropped by someone to persist in space. Now, we haven't talked about what a time step is. I don't know whether time step is 10 seconds or a minute or a day. We haven't talked about any of that yet. So let's keep this loose and abstract for now, and let's talk about details once we have an idea of what we're doing. So let's imagine that the virus, I don't know, and maybe it hangs around for up to 100 time steps, whatever that means. We'll assign some units when we're more comfortable with this. So we have a virus going out into a space. It hangs around for a while. The other thing that I need to capture is if I drop it in a space in between this time and the next time step, how much of it will spread out to the next, to the neighboring squares. And so I'll call this frac virus spread. This will be some number between 0 and 1, the fraction of the virus that's in a patch that's going to spread to the neighboring patches in the next time step. And I don't know what that is, but we're going to make assumptions for now. And again, one of the points I want to highlight is just how many numbers we have to come up with to operationalize these ideas in a model. Okay, so we have viral load, viral lifetime, virus spread. And then the last thing that I think we need to define before we go any further is the likelihood of becoming infected given your exposure to some load of a virus. So I'm going to call that prob infection given load. Again, probabilities, these are always between 0 and 1. I think this is a number that has to be really, really small. This is just my recollection from doing this before. So I'm going to make it a really small number. We'll play with this as we go. Don't know exactly what this needs to be. We'll play around with this a little bit. Okay, so here are a few parameters that I've introduced that I think are enough to help us model our virus in space. Okay, we've probably got about another 15 minutes or so of good solid programming attention. So let's see if we can get through this. And again, please ask me questions as you go in the chat or out loud. I'm happy to stop and answer questions. So one of the things I need is that I need for virus to be able to accumulate in the space. You may remember that we have people who move around, and then we have patches, which are another kind of agent who have member functions and can have properties that don't move. So every space, every coordinate in our model is its own patch that can have properties. So what I'm going to do is I'm going to write some code here at the top, patches own, which again is specifying new properties that belong to patches. And I'm going to call this load. Okay, So patches are able to have some viral load. And I'm going to make the point now at the beginning of our simulation to ask all of our patches in our simulation to set their load to be 0. So whatever number they were before, I don't want to leave it up to NetLogo to randomly decide what the load is. When we start a simulation, there's no viral load anywhere. All of our patches can have a load, but it's set to be 0. And so now in our go procedure, while people are moving around, I'm going to say those that are infected should leave some new virus. They should shed some virus in a space. And the way I'm going to do that is to say if, and so these are a set of commands that apply to all people. I'm going to ask if you're infected, okay, and the nice thing is that because I've set this up as a Boolean, or what we got true, false, if infected, yeah, I guess if I'm being really explicit, all right, if infected question mark equals true, then do what's in here. But this is actually implied. If I didn't want to write that, I'd get the same result without it. But so if infected equals true, I want you to ask the patch that you're standing on, and there's a command for that, it's patch here. Ask patch here to do something. And so inside these nested square brackets here are the commands for the patch that is being stood upon by an infected agent. And we're going to ask them to set their load to be load plus viral load is what I called it. Load plus viral load. Okay. And so Beth had a question earlier about, well, what about when you add things? And here we're doing exactly that. This set command is a basic NetLogo command that says set this variable to have this value. So we are setting the load, really parameter of or property of our patch, to be equal to whatever the load currently was, plus any new viral load from our infected person. So we are incrementing our viral load by the new load of the person standing there. Okay. So that should work. And so one of the things I can do is I can test this. Before I go any further, we still need the virus to spread. We still need people to get infected. And hopefully we'll get to all this today. But one of the things I can do is make sure that the virus is being dropped in places. So I'm gonna, this block is for our people. So I'll make a little note here. Steps for people to do each tick. And then I'm gonna have a little section here, steps for patches to do each tick. And I'm gonna ask my patches, open square brackets, and this patches here is the set of all patches in our model. I'm gonna ask them to, I want them to be colored based on how much virus they have in them so that we can see what's going on. So turtles have a built-in property of color. Patches have a built-in property of P color. So it's distinct. We know that it means the same thing. It means color, but it's for patches. I'm going to ask them to set P color to be, and what I want it to be is I want it to be a scale. I want it to be, I'm going to choose yellow if that's all right. We're going to go from black with no load up to really bright yellow if we have lots and lots of load. And so I'm going to set P color to be scale color, which is a built-in command that is expecting me to specify now what color am I talking about. I'm going to say yellow. And again, for those of you who want to look at this, scale color is right here. And this is the syntax, scale color, color, the number that I'm using, and then what the range of that is. So I would like this to be scale color yellow based on the load of that patch. And I want the range to be between 0 and some maximum. And for now, why don't we just pick the number we've specified as viral load, which is 5. So this is going to be its brightest yellow when it has a value of that immediate viral load or higher. And we're not doing anything else yet, nothing spreading, but I have written code for infected people to drop virus in the space that they're standing. So when I run this model, I'm expecting to see maybe like a yellow trail coming out behind my infected agents. Okay, and it's doing what I expected. I guess really bright yellow here is white. That's fine. So white is the brightest yellow. But that's what I'm expecting. But this virus is just sitting there. It's not doing anything. And we know that, I mean, so much of our problem has been, over the last year, has been learning about how the virus spreads and what happens with it. So we need to do a few things. We need to let the load spread. And we need to let the virus kind of die if it dies. So it happens that there is a built-in command in NetLogo for diffusion. I'm going to use that here. Let me just find it. Diffuse. Here we go. This is a patch-related command. And so diffuse whatever variable we're talking about by some share. That's the syntax. And these are numbers we've already specified. One of the unique things about this particular command is that when I use it, it's going to apply to all the patches, no matter what. I don't get to choose which patches diffuse. I don't know why they built it that way, but they did. So when I use diffuse, I don't have to ask patches specifically. It's implied, and it'll happen for all the patches. Diffuse load by whatever fraction I said was shared. Frac virus spread. Diffuse load by frac virus spread. So this line just says, use this built-in command to let that load that's been dropped spread out over space. And so now, let me check, yeah, that's happy. When I run the model now, they're going to spread it. And there we see virus is getting dropped by people who are sick, and it's spreading out over the space. And this has been easy for us to write because we're using commands that are kind of at the core of how NetLogo works. Okay. Now, the scary part about this little world we've invented is that this virus isn't going away. It's just building up, and this is going to be a scary sea of yellow in not too long if I let it go. Oh yeah, look at that. I ran it really quickly. That's terrifying. So let's add in a little bit more of what we know about viruses. They don't last forever. So our viral lifetime is 50 time steps. I think what I'll do in this block here, this is the block where I'm asking patches to do things like update their color. I'm going to use this square to ask them individually to update their load based on the idea that some of that load is it's going to go away, it's going to die. So I'm going to ask them to set their load to some new value. And the way I'm going to capture this is the idea that some fraction of the existing virus will die. And we know, so we've defined a virus lifetime, that they live about 50 time steps in this particular case. And if that's the case, then on average, we might imagine like 2%. If they live for 50 time steps, then about 2% of them might disappear or die in a given time step. That's not always true. It's not a perfect assumption, but it will work reasonably well for us. So I'm going to use a really simple mathematical equation to say set the load equal to And maybe I'll put it in parentheses here so it's clear that it's separate. The load that they have times, and then in another set of parentheses, 1 minus 1 over virus. Is that what I called it? Virus lifetime? Nope. I called it viral lifetime. Oops. Viral lifetime. So this is not a complicated expression. And I know you guys are engineering students. Math is your bread and butter. What I've done is said, so 1 over a number like 50 will be about 0.02. 1 minus 0.02 will be about 0.98. So really what I'm saying is, with this particular setting, about 98% of the load is going to persist from time step to time step here, given this setting. And we're just allowing some of it to disappear. So what I expect now when I run my model, still got a problem. Oh, you don't like this. NetLogo doesn't like to have things stuck together. It wants to have spaces. There we go. So now when I run my model, that should just, there we go. So all that virus that had accumulated before dissipated. And now we're seeing our infected agents moving around, spreading the disease. And eventually it goes away. And we made a couple of big jumps here in just a few lines of code. Nobody's getting infected yet. We haven't got there. I think that's probably what we'll do, and then we'll end. But are there any questions that I can answer at this point? It's a bit tough to do something like this over Zoom. I apologize. If we're all in a room together, you'd have it on your own screen and we could look at how it's going for everybody. It's not the easiest thing to do over Zoom, but please feel free to ask questions. Okay. All right, let's see where we can get to. Let's acknowledge that one of the things that happens now is that as this virus spreads, some of those parts of the room are kind of dangerous to be in, and there's a likelihood that we might get sick. And so what I'm going to do now in this space, we have people moving, we have people dropping virus in a space. One of the next thing I'm going to do is I'm going to probabilistically let people get infected. And the way I'm going to comment this here, I'm going to say test if infected. Okay. And I'm going to do in the same way that I did like a random draw here to decide if they turned around. I'm going to do the same thing to evaluate probabilistically if they get infected. And it's going to depend on the probability that we've defined as well as the viral load in our space. Okay. And so let's see now. I'm going to write it this way. If random float 1, so a random number drawn between 0 and 1, less than, and the way I've defined it in our space here, I define this number of probability of infection given the load that we have. So what I'm really evaluating is this, so prob, infection given load times the load that we have in that patch. So here's where there's just a little bit of I think I have to specify that the load I'm concerned about is the load in the patch that they're standing times load of patch here. I think that's right. maybe I don't need to do that. Okay, so if this, so this is my test. If random float 1 is less than the probability of infection given the load times the load that we're experiencing. Check that. Okay, that load was fine here. I thought that load of, I thought I had to specify this, but maybe I'm wrong. Okay, I'm gonna leave this for now and check this on my own time. Okay, here is a test that NetLogo is happy with, where we are checking our random draw. Is it less than the probability of infection times the load that we're currently experiencing? And if it is, then we are going to set infected to true. And now that we've done that, what we expect is that we're going to start to see more agents getting infected over time. Now, I don't know, I kind of made up numbers here. I don't know whether this is a particularly likely thing. Let me ramp this number up. So now I'm making it more and more likely that people get infected. Maybe I'll ramp up our virus load as well. It's a little bit hard to see whether people are getting infected. So what I might do instead, and let me add in a plot. This is a graph. I apologize, the text here is a little bit small. I want it to count for me, just for now, a really simple pen is what it's called, a plot. Count people with infected equals true. Set my model and run this. Okay, so now this, we're sort of flatlining here. Nobody's getting infected. Oh, there we go. So a new person got infected. Oh, there's another infection. Oh, it's picking up. Okay, so with more and more people being infected, the viral load in the space increases. We'll see if that ramps up. Maybe I need to speed this up over time. There we go. Okay, so we're starting to see more and more agents getting infected over time. And now this is really picking up. Okay, we're in a terrifying world of white infection here, and we're up into sort of like just super growth. We had exponential growth at first, and now I guess we maybe don't have as many people infected. Oh, I realize what my mistake is. We have people being infected. What I need to do is in each time step, check if people are infected. I need to update their colors. If infected, set color red. And we'll have to update this because we have other states. Oops. Okay, so now as our agents are getting infected, more and more of them are turning red. So all of our red agents now are the agents that are being infected. And the shape of our curve is slowing down a little bit as we have fewer and fewer susceptible people to get infected. So now we've captured this first part of the curve, this basic idea of people getting infected. Now we've kind of topped out, and that's our curve. Looks like just about everybody's infected, except for these two fortunate individuals. Okay. So that's not the only thing that happens. We get infected, and then we may recover, we may not. And if we recover, we may have some immunity over time, and that might prevent us from getting sick again. So we've got to add those things in. I'll tell you though, we've kind of already done most of the work. So it didn't take much code to capture a lot of what's happening. Does everybody have the brain power for about another 10 minutes of coding? And then we'll wrap up and look at what we got and plan to meet next week. Within 10 minutes, I think we can add in mortality, we can add in recovery, we can add in immunity, and we can look at how those curves move over time. So if you've got the brain power for that, let's plug through. And of course, even if you don't, you can just log off now. It's being recorded, and you can pull it up again on Sunday morning with a cup of coffee and come back to it. Okay, so what I need to do is I'm checking that people could be infected here. I need as well to let them possibly recover. So test if recovered. And this code is it's gonna look similar, but what I need now, I need some more numbers. I don't know how long it is that the disease persists. We know in it's maybe a week or 2 weeks we stay sick. I don't know what a time step means here. Maybe it means a few minutes. So maybe 2 weeks is like 100 or 200 time steps or 1,000. I'm going to define a slider for us so we can capture the idea of, I'll call it recovery time. So how long it takes to get better once you're sick. And I don't know whether it's 100 or if it's 1,000, maybe it's somewhere in there. Again, we haven't defined what our time step is yet. So we'll be a little bit loose with that. So we might recover. The other thing that we need to capture is our mortality rate. And this is something that, it depends on a lot of different things. One of the best ways we have of reading about this, one of the ways this is best reported is in our case-specific mortality rate, so our case mortality rate. And this number gives us, given that you're sick, it's the likelihood that you won't survive. It's the likelihood that you will die, given that you're sick. And I think it's probably something like somewhere between about 1% and 5%, depending on what's going on. So I'm going to put a number like this. And so this is, given that we're sick, it's the likelihood that any time during our illness, we're gonna die. Okay. I think those are the numbers I need for now. I also need to expand a little bit on our properties. So let's imagine, oh, maybe we need one more number, and that is once we've recovered, probably for some time, we're immune. I don't know how long that is. Maybe it's no time at all. Maybe it's 1,000 time steps. Maybe it's longer. I have no idea. But let's just wait. We've got a recovery time. We've got an immunity period. Okay. I'm going to add more properties here. So we have a property for whether or not we can be infected. Let's also make note of when we got infected, so we know how long before we probably recover. And then I'm going to have another property of, are we immune or not? And if we are, we're going to make note of when we recovered. Okay. So we now have these properties of, am I sick or not? Am I immune or not? And when did those things happen for me? Okay. And so what I'll also need to do is, when we're infected, when we get infected, I'm going to set those values. So set infected time to be ticks. Whatever our current time step is right now, that time is going to get recorded as the time we got sick. And I need to remind myself, I probably have to, do I need to reset that at the beginning? No, I think okay. All right, so my initial infections, they also set infected time. So those of us that got sick in the beginning. Okay. All right. So let's test if we are recovered. So if we are infected and the current time is enough past the time that we got sick. So the current time minus our infected time is greater than, what did I call this? Our recovery time. So if we are infected, but enough time has passed that it's been longer than the time we expect people to stay sick, let's let them recover. So inside this block are my instructions for these agents, and they are set infected to be false. We're no longer infected. And then let's set immune to be true. And that's also set recovered time to be ticks. So we have this measure of when we recovered and sort of when our immunity started. And so you can imagine there's a similar test we ought to do now. Oops, I gotta close this parenthesis. There's a similar test to see test if still immune. Okay. So if we are immune and it's just the same, the current time step minus the time when we recovered is greater than our immunity period. I think that's what I called it. Then in this block, set immune. So just a little bit of, let's do a little bit more color work here. If infected, we're going to let people be red. Let's say if immune, let's let people be blue. And then let's say if, we could do this as an if else, but I'm going to just be really explicit here. If infected equals false and immune equals false. So we're neither infected nor are we immune. Let's just go back to being green. So we'll run our model now. Why is this problem? Apologies, give me just a moment.
What's that?
Every now and then. Every now and then. Okay, so if, maybe this is the way to write it. If infected, if not infected, and not immune, I'm gonna
Dia sejak mulai nanti itu kenalnya suka atau
Apologies as we go. Every now and then, I break my own rules. As I mentioned, if you change too many things before you check, you'll never know what went wrong. There we go. Okay, so it's happy now. NetLogo didn't like something I wrote here, so I just was more explicit about it. Okay, so if infected equals false, apologies, I'm just going to ask if you can keep your microphones muted. Thank you. Okay. All right. Okay. Now we have a model in which people can get sick and they can recover. And we're starting to see that here in our plot. So we see a peak and we see a loss of infections, and then we see another peak. And then it looks in this case like the virus has cleared out of our space. So maybe one of the things we can look at, I'm going to add to this plot, and I think we'll stop here because we've kind of hit our time, and we'll continue this in our next day. I'm going to add another pen. This one's going to be gray. So here I want to plot the count of people with immune equals true. Let's change the colors here. Let's make that blue. And then let's make our infected red. Okay. So now we'll set up our model, we'll run. Okay, so we've got infections in our model. People getting infected, recovering, we're having immunity here. So depending on a lot of different things and how we parameterize the infectivity of the model, how we manage the viral load, we're going to change who gets sick at once and how long it persists. But we've got some basic machinery in here now for people to get sick and recover. We don't have people dying, and we don't have any kind of behavior in here, but it's a nice start. We've been at this for now about an hour and a half. So I want to stop there and maybe ask if you have any questions about the things that we've done so far today. I'm going to go ahead and save this, and I'll upload it for you to be able to access from our shared document. Any questions about the things that we've kind of touched on today? It's been a lot of things. We're a quiet group. So I'll share this model, and you can play around with the parameters and get a sense of just how different the model behavior can be with small changes in parameters. But perhaps what I'll do then is say, okay, so we made it through a lot of what I expected we would do today. Didn't quite get to finishing our model transmission. We had a bit of a shortened time period today. But I'll share the link to our Kumu model. I'll share this file, and I'll encourage you, play around a little bit. I'm going to suggest a few things you might try, and I'll list them here. And then otherwise, we're going to meet next week at the same time. We'll finish this basic model, and then what I'd like to do is try to think about ways we can represent interactions among people. And we'll do that at the beginning of the next week. So thanks very much for your attention. I know it's been a while and it's Friday afternoon. I'll share the recording as soon as I can, and I'll look forward to hearing from any of you over email or in an office hour appointment.
Thank you so much, Andrew, for that very nice presentation. Actually, the presentation has been very great.
Good.
Have also been following here. I have followed. So I was telling myself, oh, I'll need this file and do a lot of practice. Actually, that is what is needed. And I know the students will also need that, so that we have it, do it yourself, maneuver through the model and come to the end where you've just ended. So it was really a nice presentation. I can tell you that we have some of our students, like Kiplono. Kindly, Kiplono, I'll ask you to say something because I want you to lead this in the group. I'm seeing he's doing very nice things and sharing on the group's WhatsApp forum. That's Kiprono Cheruyot. We are happy about the work that you're doing. Kindly keep up, and kindly take the other students through this. I know some of the students don't have the basics of the modeling, but I saw that you have. Kindly bring them on board. This is very interesting, even for taking your projects, which will be coming in the coming next few months. So Andrew, we are really honored to have you on board. I know some of the students will be taking search for the projects. We'll still be having you for the supervisor. Kiplono, I'll not talk all, I'll ask you kindly to talk, to give something, an overview of what you're finding or the application. Kiprono Cheruyot, please. Yes.
Hello. Okay, what I have to say about this presentation, it was an awesome. And what needs to be done is practice, as you have said, and what Dr. Andrew has said is awesome. And what you find that people might find it hard, because even me, myself, I don't have the basics for programming. You see, somebody without that, you won't be able to format it well or code it well, this model. I can say it's a nice presentation, and everything is awesome. What we need is just playing with it, because you find that I played with what is in Epidem, travel and control. It was awesome. The coding they put there, it's awesome. It's just a matter of practice. It's not that hard.
Yeah, no, that's a really good insight. And I feel like the experience is very much like when you're trying to learn a new language as an older person and just needing to walk yourself through hard sentences and understand what works about them and what doesn't. And it just takes time. And it's a very difficult thing to do over Zoom. But to the extent that you find this exciting, then we can find time and space to do some more intensive in-person development work later on in the year. So we'll see you next week then, and hopefully, you know, we can make some time next week to start the conversation about, you know, this COVID is great, right? It's a great thing to model, but it may not be the things that you're interested in modeling. And so what are the kinds of problems to which you could imagine applying this kind of approach?
So thank you very much, Andrew, for the session, for today's session. We are looking forward to meeting you again next week on Friday. To the students, we have a whole week between now and Friday. Kindly practice, practice, practice. Play around with the model, and by Friday you'll have made quite some advancement in what you are doing. Once you get it, and it will never go. The students will be starting their projects in, I think, the next coming 4 months. For those who will have shown interest in modeling, we'll be able to plan with Andrew if he'll be available to come over and do one-on-one coaching for those who will be taking it for their projects. So let me take this opportunity to end the meeting now. And again, thank you so much for your time and commitment to have us on your busy schedule.
Perfect. thank you so much for your attention, and I look forward to seeing you guys next week.
Thank you so much, Andrew.
Bye.
Bye.